In the introduction, we talked about how ammonia is toxic to cells and how ammonia is generated from glutamine. Let's take a look at how this glutamine is converted to glutamate and generates ammonia. Okay, so we have an active site in our enzyme. There's believed to be some nucleophilic component, and there's an acidic component in there. Now, what happens is glutamine inserts into the active site. So this is glutamine. I drew it in its form that would exist at physiological pH. Okay. So in the first step, what happens is this nucleophile in the active site attacks the carbonyl carbon, and the carbonyl carbon then becomes protonated. And this goes on to become, here's our glutamine part. And there's our active site, and there's the conjugate base from there. And there is also another acidic site. Now in the second step, what happens is the conjugate base of our acid from the first part deprotonates the tetrahedral intermediate. It starts to collapse and kicks out this NH2, which becomes protonated by another acidic component inside the active site. Okay, so this then goes on and becomes active site. There's our nucleophile. So in this step, like I said, the ammonia here got kicked out, so that generated NH3. That's the source of the ammonia that we'll use for amination reactions in subsequent steps. Okay. So you'll recognize this as a form of covalent catalysis, right? We've seen a mechanism similar to this. The mechanism of proteases go by a very similar mechanism, right? Covalent catalysis and general acid-base catalysis. So there's some general acid-base catalysis and then some covalent catalysis. Now, if you hydrolyze this with water, you'll generate glutamate. So this is glutamate. So let's look at some evidence for this mechanism. Okay, and some evidence for what could possibly be, what could this group here possibly be, that nucleophilic component. Okay, so evidence for covalent catalysis. Now we have this acyl enzyme intermediate. I'm just going to reproduce it here. This looks a little messy here. This was my ammonia group. And one typical thing to do with acyl intermediates is to react them with hydroxylamine and H2OH. Hydroxylamine is a very good nucleophile. what hydroxylamine will do, it will attack this carbonyl carbon and do an acyl substitution reaction, go through a tetrahedral intermediate. I'm going to show my cheater mechanism here, and then eventually kick out this X group to generate a hydroxylamine derivative of the glutamate. So that's decent evidence for covalent catalysis. There's obviously some other evidence that they found as well. Other evidence includes using reagents like this. This is an inactivator. It's an inactivator. And it typically inactivates cysteine bonds. What happens is if you have some cysteine residue, I'll show it as a thiolate here. Okay. What it will do is it'll attack here as follows and generate an acyl tetrahedral intermediate. Oops. Like so. And this then attacks here as follows and kicks out this iodide and makes an intermediate that looks like this. So this, like I said, this reagent here, this is called iodoacetamide. And it's a potent inactivator, typically for cysteine thiolate systems. Okay. So what they did then was they did what's called Edmond degradation. And what Edmond degradation essentially is they break this enzyme apart, and then they can find these cysteines with this piece on there. And so they saw cysteines that had this piece like this attached to it. Let me write this a little better. So cysteine, sulfur, like that. So they isolated this. So that indicates that X, back in this mechanism here, this X is likely a cysteine bond. Well, I'm sorry, not cysteine bond, I'm sorry, a thiol of a cysteine residue. Okay. Okay, so that's essentially how the ammonia is produced in these amination reactions. Again, kind of start from the top. Glutamine enters the catalytic site. There's a nucleophilic residue that turns out to be a sulfur residue. Let's put an S over this so we can see it. That sulfur attacks, gets a tetrahedral intermediate. This tetrahedral intermediate collapses. Both of these are supported by or facilitated by general acid-base catalysis. Upon collapse of the tetrahedral intermediate, we generate our ammonia fragment, which is going to be used in later reactions or a subsequent reaction. And then that generates a covalent enzyme acyl intermediate. So this is an acyl enzyme intermediate. And then that acyl enzyme intermediate can hydrolyze off and generate glutamate and regenerate the active site to start the catalytic cycle all over again. Okay. Okay, with that said, then let's in the next video we'll take a look at how this the ammonia that's generated, is used to aminate various products.